Hello everyone, welcome to a new lecture of our course on heterogeneous systems. Today we are going to introduce another parallel pattern, graph search. This is going to be one more after a few parallel patterns. We started with reduction, an operation that reduces a set of values to a single value, and we discussed ways of implementing reduction with a divergence-free mapping in order to maximize warp utilization. Next, we covered histogram computation. It's a computation used for reducing the dimensionality and extracting notable features of large data sets. In histogram computation, we have to compute a histogram that is composed by bins or counters that we increment every time we find a value in the input that corresponds to the value of the bin. In a histogram calculation, we have to typically use atomic operations, and because they cause serialization, we discussed a way of alleviating the cost of this serialization. That's the privatization. Today, we are going to talk about privatization again in the context of graph search. Next, we talk about the convolution, which is an operation where we apply a filter or a mask on each of the elements of an input in order to compute a weighted sum, and that is going to be the output. Convolutions are very much used today in machine learning and artificial intelligence, for example, as convolutional layers, but they can also be implemented for 1D or 2D or 3D inputs. In the case of 1D, commonly used for audio processing, as you can see in this example, we are applying a mask M on each element of the input N in order to compute partial products, then reduce them and store in the output array P. The convolutional layers are typically reduced to matrix multiplication that requires unrolling the input feature maps as well as the convolution filters. And this way we can perform a matrix multiplication that is very well optimized for GPUs using techniques such as these joint register and shared memory tiling that we introduced in another lecture. The next pattern that we covered was the prefix sum, an operation where we are computing the output recursively based on the previous outputs, and that can be either computed in the exclusive or inclusive manner, depending on whether we are including the input value corresponding to the same index. We discussed a way of implementing scan in a hierarchical manner with per warp scan, then per block scan, then the sum of partial sums that this scan of partial sums can be done typically in the host or in another kernel, and then the final addition step. That was the SSA version of the scan operation. We also discussed the reduced scan version of the scan operation. And in the last lecture, we talked about the sparse matrices. We discussed different compression formats. For example, these CSR, which consists of an array of row pointers, and each row pointer points to a column array where we store the column indices of the non-zero values. And then we also have another array that is the value array that contains the actual values of the non-zero elements. Sparse matrices are very important in today's lecture as well, and we are going to use them in graph search because graphs are usually very sparse. So we will need to use compression formats as well to store the information about the graph, as we are going to see. Graphs are very much used in problems where we need to do dynamic data extraction, because the data needs to be processed in multiple phases, and in each phase, the amount of computation might change. This happens in graph algorithms that are used, for example, in many different fields, like, for example, electronic design and automation, optimization problems, etc. And in this lecture, we are going to use breadth-first search, or BFS, as an example. Parallelizing dynamic data extraction has important challenges because the data is not going to be so easily laid out for locality, coalescing, and contention avoidance. And that's something that we will have to figure out how to do it. And we are going to discuss some ways in this lecture. And the other challenge is that the amount of parallelism, the amount of work grows and shrinks in each phase of the computation. If you think, for example, about graph from a social network, there will be many different vertices, and each of the vertices will have a number of neighbors or a number of friends in the social network. And there are people who have very few friends, while there are many other people who have a lot of friends. So depending on that, we are going to, depending on which node or what vertex we are processing at the time, we will have to exploit more or less parallelism. As I said, graph and sparse matrices are closely related because graphs are represented as an adjacency matrix. And the way to compress this adjacency matrix is going to be using one sparse matrix format. For example, the compressed sparse row that we are using as an example here for this adjacency matrix. Same as we have in the previous slide for CSR, here we have an array of row pointers that contains the source vertices, and then this array of row pointers points to the array of column indices and that are the destinations of each edge, and finally the array of non-zero elements. In this case, all elements are 1 because this is an unweighted graph, so all edges value the same. Okay, let's start with breadth first search. The goal in breadth first search is to determine what's the minimal number of hops that is required to go from a source node to a destination node or all destination nodes. For example, if we have this graph and our source node is node 0, as you can see, there will be different distances or hops to each of the other vertices of the plot. For example, these 2 vertices are at distance 1 hop, these 5 vertices are at distance 2 hops, and this vertex 8 is at distance 3 hops. There are different approaches to parallelizing graph processing this computation that we have just seen for BFS. One of them is the vertex-centric approach. In the vertex-centric approach, we assign one thread to do something for each vertex. So we are assigning one thread per vertex, and we will typically use CSR or CST compression formats for the graph. The reason is that given a vertex with these formats, it's easy to find all its neighbors, and that's what we need to do when we are computing BFS. But there are 2 different ways of applying the vertex-centric approach. One of them is called top-down, and the other one is bottom-up. There is a difference. In both cases, we assign one thread per vertex, but in the top-down approach, what we do is that we start with a single vertex, which is the source, and we create a frontier, which are the next vertices to be visited, the vertices to be visited in the next iteration of the algorithm. For example, for vertex 0, the first 2 neighbors are, or the 2 neighbors are vertices 1 and 2. So we will put these 2 in a queue, and we will process them in the next iteration. They will be in our input queue for the next iteration, where we are going to discover the neighbors of these 2. This top-down approach is the one that we are going to explain in more detail in this lecture in the later slides. For the bottom-up approach, the approach is different. In this case, we also have one thread per node, but what each thread is going to do in each iteration, the thread is going to see if for the own node or vertex, any of the surrounding neighboring nodes or vertices has been visited in the previous iteration. If that's the case, this one is marked as belonging to the current iteration. So those are the 2 approaches, top-down and bottom-up. As you can see, there is more constant work in the bottom-up approach because all threads are active in all iterations, at least in the beginning, while in the top-down approach, we will see how the amount of work grows or shrinks depending on the exact phase or exact iteration of the computation. The other approach to parallelizing graph processing is edge-centric. In the edge-centric approach, we assign one thread per edge, and we do some calculations for that edge, like finding what are the source and destination vertices, for example. They typically use, the edge-centric approaches typically use COO compression format because given an edge, it's easy to find what's the source and the destination vertex. And then there are also hybrid approaches. For example, given an edge, we need to find both neighbors. So for each edge, both the neighbors of the source vertices and the neighbors of the destination vertices. And in this case, it will be good to use both COO and CSR or CSC. Okay, so let's put the focus on BFS, the vertex-centric approach, top-down approach. We start with the source node. In this case, is node 0, and we are going to identify and mark all nodes that can be reached in 1, 2, 3 hops. Those are the nodes that are going to be discovered in each successive iteration of the BFS algorithm. So in the first iteration, we find vertices 1 and 2, and we put them in the output queue, and they are going to be used for the input queue as the input queue for the next iteration. In the second frontier, we find the neighbors of 1 and 2. In this case, are nodes 3 to 7. We enqueue them in the output queue, and then we go to the next iteration. In the last frontier is going to be only node 8. So that will be the final outcome, the final solution for breadth-first search with node 0 as a source. We could also have other nodes as the source, for example, node 2. In this case, the frontiers are going to be different, but in the end, after several iterations, we will reach to all nodes in the graph. Now, when it comes to processing a frontier, we have to visit the source array, the destination array, and finally an array of labels where we are going to mark what's the iteration or what's the phase of the algorithm where one specific node was discovered. So imagine that we have 2 nodes in the frontier, in the current input frontier. These are nodes 0 and 8. First of all, is go into the source array where we find what's the pointer that corresponds to each of the 2 nodes in the frontier. In this case, for node 0, we know that we'll have to go until element 2 in the array of destinations, while for node 8, this one doesn't have any nodes, because any neighboring nodes, because this is a directed graph. There are no neighbors of node 8 in the destination array, or those neighbors could be around here, but they don't really exist. So for node 0, we visit nodes 1 and 2, and we are going to put them in the corresponding output queue, and we can mark them as visited in this iteration. In this case, one of them was node 2, that was the source, so that one was at 0 hops from the source, which is the same one, while node 1 is at distance 3 or 3 hops. We can parallelize these naively, let's say, with a complexity of O, V plus E, being V and E, the number of edges and the number of vertices and the number of edges, assuming that we have 3 nodes in the frontier, 5, 6, 7, one thing that we can do is assigning different threads to different nodes in the queue. We dequeue them in parallel, and now we check what are the neighbors. Observe that node 5 doesn't have any neighbors, node 6 has 1 neighbor, which is node 8, and node 7 has 1 neighbor, which is node 0. So these 2 need to enqueue the neighbors in the output queue. But in order to do so, and in order to avoid a conflict, we will have to, or a data race, we will have to use an atomic operation. Update one global counter. This will give us an index where both threads need to write the corresponding element. And if they do that, the result will be correct, or the output, the enqueuing process will be correct, but because we are using atomic operations, we have serialization, and this really hurts the performance. We have already seen how to deal with atomic operations, and one way is called privatization. We already explained it in the histogram, the lecture about histogram calculation. Here we are going to use it in a different way. Instead of having a single queue for a single output queue for all threads running on the GPU and processing one specific iteration of the graph algorithm, what we are going to have is local queues. These local queues, as you will see, are going to be in the shared memory, and every time that threads in one thread block find new neighbors and need to include in queue in the frontier these nodes, they will do it in the private queue. And at some point, they will find when the private queue is, when the iteration has finished, or when the private queue is complete, we'll have to find what's the location to write in the global queue by basically updating a global counter that is accessible by all thread blocks. We could also do a scan operation here if we know the exact number of elements, the exact number of nodes that each of the local queues have. So that's the way of building the next frontier hierarchically. We first create the local queue, we then create the global queue. And this is what we call the two-level hierarchy, where with the block queue that is typically residing in shared memory and the global queue that resides in global memory, and where we will normally insert the elements or the nodes in the block queue only when the block is complete, when the computation of each block finishes. Still, we will have collision in the B queues. It won't be so harmful as the collision in the global queue because now we are using privatization and because shared memory is faster, but still there might be heavy contention in some cases. Still, we could also add additional levels to this hierarchy. We could have warp queues, for example, or even thread level queues. That will always depend on the amount of memory that you have, or the amount of registers that you have, on chip memory in general, and the specific complexity of the algorithm and the graph. We are going to launch. So by default, we will launch multiple iterations, and for each iteration, we will launch a new kernel. So we need to create a global barrier to do so. And the way of creating a global barrier, as you know, is to terminate one kernel. And then a next kernel call for the next iteration of the algorithm, we terminate the kernel, a new kernel call, etc. These kernel termination and relaunch might have too much overhead. So there are some solutions that have been proposed, like for example, using a hierarchical, a multi-layer kernel arrangement where we have different types of kernels depending on the specific characteristics of the frontier, as we are going to see, basically depending on the size of the frontier. But there are other solutions such as dynamic parallelism that we are not going to talk about today, but we will cover in a later lecture, and persistent threads with global barriers that we are going to briefly mention at the end of this lecture. So in the hierarchical kernel arrangement, we are going to have different kernels based on the size of the frontier. We, for example, can have one kernel that uses intra-block synchronization only for very small frontiers. We don't need to use all GPU cores or many GPU cores. We can just use one GPU core and one thread block, and this thread block can use sync threads for the threads to synchronize. But at some point, we will have larger frontiers. Remember that here, the amount of parallelism is very dynamic. So we will have a larger frontier, and we will need to launch a bigger kernel that we will have to finish when the frontier, the output frontier is complete, and relaunch a new kernel. So those are basically the two approaches in this arrangement. In the first one, as I said, the small size frontiers, we just have a single thread block. When these thread blocks create the block queue, they synchronize using sync thread, and then we can go to the next level. And then again, new queue, this propagates through multiple levels, and it will be pretty fast because we are only using accesses to shared memory, no accesses to the global memory, and because in the end, the atomic operations in shared memory are also faster, and we need to use them to enqueue in this BQ. But at some point, we will have to use the kernel termination and relaunch to implement the global synchronization for big-sized frontiers. In many cases, these kernel launch overhead will be acceptable if there is more or less a significant amount of computation inside the kernel. But if it's something as simple as VFS, where we are just checking some values from memory, simply accessing memory, and maybe updating some labels eventually, we may not have so much computation, and these kernel launch overhead might be still significant overhead. With dynamic parallelism, as we will discuss in the corresponding lecture, there might also be overheads, but at least we won't have to terminate the kernel. We can launch new kernels for the children or for the neighbors of each existing node. And the last solution is to use persistent threads and interblock synchronization. In this case, it's like combining kernel 1 and kernel 2. We are going to avoid the kernel relaunch by doing global synchronization that we are not covering in detail in this lecture, but you can learn about it in the longer version of this lecture that I will share in one of the final slides. Basically, the idea here for persistent thread blocks is that instead of using as many thread blocks as we need to cover the entire input frontier, in this case, we are talking about M thread blocks, we are going to launch only as many thread blocks as can run concurrently on the existing GPU cores. For example, in these two GPU cores, SM0 and SM1, they can only fit one block or two blocks at a time, so only 4 thread blocks. So what these 4 thread blocks are going to do is process in the frontier, and then when they are done with the first chunk, they go to the next chunk that is available or to process in the frontier. Observe how block 0 first starts here. When it's done with this part of the frontier, it goes to this part of the frontier, and so on. Good thing is that now we don't need to synchronize by terminating the kernel, because the 4 thread blocks in this example are active at the same time, so they can synchronize using atomic operations to global memory. In the longer lecture, as I said, we explain a way of doing this global synchronization. This is just one way of doing so. There might be other different ways, but with similar spirit. There is also a minor bug in this code. There is a thread fence that is needed here, but it's removed for simplicity. But if you're going to use it, please keep that in mind. And if you want to learn more about graph search, graph traversal, or graph processing in general, you can check chapter 15 of the book, Programming Massively Parallel Processors. That's all for today. I hope that you found the lecture interesting. Thank you very much for your attention, and see you in the next one.